Hi everyone, welcome to section 1.4, Introduction to Limits. The learning objectives for this section would be to find the limit of a function at a point from the left and right hand side, infinite limits, be able to find limits in three ways: graphically, table of values, and algebraically. Find limits using the direct substitution property correctly. Find limits at positive and negative infinity, and find functions, vertical and horizontal asymptotes using limits. Okay, so we'll start with the informal definition of a limit of a function at a point. So, definition informally. So, the limit of a function, right, f of x, as x approaches some x value, right, a is some x value, is L. L is just some number. Could be 2, 3, 10, 1/2, right? But that's really the informal definition. Limit as x approaches a of f of x equals some limit L. So if we can get as close as we like to L with f of x, our function, by taking x sufficiently close but not equal to C, this should say A. Okay, just getting really close to A. We're going to see what that limit gets to. So let's take a look at the graph of f of x equals x squared minus 2x plus 3 for values of x near 3. So we're looking at near x equals 3. Okay, so what we're going to do is jump to Desmos and graph this thing. So I already have it here, right? In the red, here's x squared minus 2x plus 2. Here's what the graph looks like, and you could do the same as well. So what I'm going to do is jump back to our notes and paste this graph. So go ahead and paste it right here. So let me adjust this a bit. Okay, so here is our function, right, from Desmos. So I'm going to zoom in a bit, but it's asking us for, we're looking at the function at values near x equals 3. So I'm going to zoom in, right? Here is x equals 3, and I want to see the values that are near our function is at when we're at x equals 3. So let me kind of draw this, you know, trail up here. So what values is our function at x equals 3? Oops, sorry about that. 1 second. Okay, welcome back. So as x equals 3, right? Erase this a bit. As we're coming up from x equals 3, what value is our function at? It looks here that our function is at 5. So that means our limit is going to be 5. Okay, that's where our function looks like it's at x equals 3. So graphically, we were able to figure that out. So what this next statement says is when x gets close to 3, right, which is exactly what we did, f of x is close to 5. And so we write the limit as x approaches 3 of that function is going to be equal to 5. Okay, so something important to remember, we'll get this out the way, is that a limit does not need to depend on the actual value of the function at that point. So it does not actually have to depend on that. And we'll see that what that means in the next example. So let's look at the graph below, right? We don't really know what it is. We just are given a graph, right? So let's go ahead and find like the limit of each of these desired question. So the limit as x approaches 2 of f of x. So once again, we're looking at when x equals 2, what is our function near at? Well, it looks like it's near 3, right? If we kind of trail over here, looks like it's at 3, right? That's where it looks like it's trending to. So this would just be equal to 3. Okay, so let's check out when x approaches 3 now. So same thing. Here we go. It's right there at 4. So this is equal to 4. Okay, but notice that we have these really holes right here, right? These are considered holes. So it doesn't really depend on the value at that point because this is technically f of 2. It's a solid point. That's where the function is defined at for x equals 2. But the limit is actually 3. It doesn't depend on the actual value. So that's what it means that they're just talking about the behavior around that point, not necessarily what that point is, what that output is. So that's how limits kind of work. It doesn't really depend on what the value is. Okay, so let's keep going. Let's take a look at another example. So like in this example, you can always try graphing to help find the limits, right? Graphing always helps because you just get an overall picture of what's going on. So let's use a graph and a table of values to find the following limit. We'll get to the table of values in a second. So here's this function, right? And it says it wants us to graph the function. So once again, what we can do is just go to Desmos. So Desmos is right here. I have it typed in already in the second one right here. And so this is what the graph would look like. Okay, so just a couple of key points to plot for us. Looks like it's 0, 1. Just gonna label that, and then it looks like you have -2, possibly. Yeah, -2, -1. That's okay. So let's jump back to the graph and actually plot this thing. So here we go. We have a good point here at 1, 1. I'm sorry, 0, 1. And a good point here at -2, -1. Okay, so the graph generally looks something like this. Okay, and then went up sort of like that, and then also like that, and like that. Okay, so this is the graph, right? So once again, we're checking out the limit as x goes to 1. So where does the function go as x goes to 1? So we're just going to check out at x equals 1. So kind of approximating right here, we can kind of approximate that, it's like 0.5. So the limit as x goes to 1 of this function is going to be, this looks like 0.5. So I'll say something like f of x goes to 0.5. Okay. And just meaning f of x is just a function we're checking now. So it looks like it's going to 0.5, right? So that's just checking it out graphically. Okay, so now what about a table of values near 1? So what we're going to do is actually just plug in all these numbers near 1. It could be a little before, like 0.99, a little after, like 1.001, right? Think about kind of like a number line. Here's 1. We're just picking points like 1.001, 1.01, and then, 0.999, and then etc. Just picking points at and around 1. Okay, so we're just going to plug these into the function, right? We're going to plug these into this function right here, and we're just going to get a couple of values. So if I plug in 0.99, I get 0.503. you plug in 0.999, you should get 0.5002. And then if you go on the other side and plug in 1.001, you get 0.49975. And for 1.01, you get 4.4975. Okay, so these are the values we get, okay? We just plug in a bunch of points near one. So here's the next question, like why can't we use x equals 1? So why can't we do that? Let's actually check that out. So if I plug in x equals 1 into that function, so f of 1, right, it will be 1, sorry, it will be 1 minus 1 over 1 squared minus 1. Okay, so if I work this out, I get 0 over 0, which is just not 0, right? It's going to be undefined, right? Remember, if anything is being divided by 0, it's undefined. So that's why we actually can't plug in 1. That won't help us at all. Okay, but just looking from this table overall, right? What does a function do as x goes to 1? Let's kind of come back over here. What does it look like it's trending towards? Well, over here, it's like getting really, really 0.49. Over here, it's going really 0.5, but not exactly 0.5. But once again, these values get close to 0.5. So one thing you can say here for a formal answer is that as x approaches 1 of this function, x minus 1 over x squared minus 1, it equals 0.5. Okay, so, oops. So either way, with the table or a graph, we get the same limit for this function. But one thing to remember, kind of backtracking off of what we went over on the previous page in the highlight, that the limit does not equal when we plug in that point, since it's not defined at 1, right? So those are two ways to figure it out. And there's one more way to figure it out. We can also just use algebra to figure this limit out. So what I mean by that is we have the limit x approaches 1 of x minus 1 over x squared minus 1. We actually have this, we actually could solve this limit algebraically. So what does the bottom factor into? Well, the bottom is x squared minus 1. What that actually factors into is x plus 1, x minus 1. Okay. And then you have x minus 1 up top. So now you can see that these two will cancel out. And you end up with limit as x approaches 1 of 1 over x plus 1. Okay. So now if I plug in 1, I will not get a 0 on the bottom, right? If I plugged in 1 over here, I got a 0 on the bottom, which is what happened in that undefined situation. But now I can actually plug in 1. So I'll get 1 over 1 plus 1. Let me use a different color. I get 1 plus 1, which is 1/2, which is the same thing as we got 0.5. So that's another way to figure it out. So if you can solve some algebraically, yes, you can do it. If you have no other options, my second option would be graphing, and last one would be table of values, but we rarely have to use that unless asked. So it's kind of like 1, 2, and then 3, kind of the way to go about it. Okay, just a couple of things in mind for limits when we try to solve them. You always need to I'll say it like this, limit rules. Limit rules One, always need to write limit as x approaches a. You always need to write that until you plug in x equals a. You always need to write limit of that, right? Second thing, never write limit as x goes to a equals whatever you're like working with. Okay. So that's another thing you can't do. It's like mathematically not correct. The limit is always like attached to whatever you're working with. So I can't write limit equals that, right? That's just not correct. So always need to write that. And then, yeah, so those are just two main limit rules. So in your work, you might make a mistake like these, and I'll make a note of it. But yeah, like mathematically, it's just not correct. But okay, so that's it for this video. I'll see you in the next one. Thank you.